What's going on, everybody? High Peak Education coming at you with another educational video here for you today. This time we're looking at magnetism and how it affects the motion of charged particles, namely magnetic forces. That's today on High Peak Education. I would like to talk about a magnetism problem where we are able to calculate using Earth's magnetic field what the speed of a proton must be for it to remain at a constant height. A proton moves eastward in the plane of Earth's magnetic field so that the distance from the ground remains constant. What is the speed of the proton if the Earth's magnetic field points north and has a magnitude of 5.0 times 10 to the minus 5th Teslas? Okay, so first of all, let's figure out what our unknowns and knowns are. Always a good idea when solving a problem. The speed, that's the magnitude of the velocity, is here, and that's in meters per second. We'll solve it. The magnitude of Earth's magnetic field is 5.0 times 10 to the minus 5th Teslas. That's SI units for the magnitude of Earth's magnetic field. That's a pretty typical value. That's about 1/2 of a Gauss. You will sometimes also see that unit used. The mass of a proton is something that you should be able to look up. To 3 significant digits, we know it now experimentally to be about 1.67 times 10 to the minus 27th kilograms. We also know the charge on a proton is the so-called fundamental charge, and that fundamental charge is about 1.60 times 10 to the minus 19th coulombs. That's the same magnitude but the opposite sign of a charge for an electron. Well, we are needing to set up a coordinate system. If the charge is moving eastward, let's call that the positive x direction. If the charge has a northward Earth magnetic field impingent upon it, that is, the Earth's magnetic field is moving in the positive y direction. The x direction is the direction of the proton movement, but the y direction is the direction of Earth's magnetic field. So this is how we depict it three-dimensionally. East is the direction of the proton movement, north is the direction of the Earth's magnetic field, and then upward is the direction of maybe some forces, and that we'll call the positive z direction, because x pushed into y, or the right hand rule, says that that's going to be the direction of the positive z axis. So if the particle stays at a constant height, that means there's zero net force on it. That is, the weight downward, mg, and the magnetic force, F sub b, upward, should balance. That is, when you add them together in the vertical, in the z direction, you should get 0. So Fb minus mg is 0. M here is the mass of the proton. G is the gravitation constant. For Earth, we know that to be approximately 9.8 meters per second squared in SI units. What is Fb? Well, that's the magnetic force on a charged particle in a magnetic field, which is QVB sine theta. Q is the charge on the proton, that's fundamental charge. V is what we're trying to solve for, the speed. B is the Earth's magnetic field magnitude. And then sine of the angle between them, theta is the smallest angle between the velocity vector of the proton and the Earth's magnetic field vector direction, which in this case, if you view looking down on the east and north plane, that is the x and y plane, theta is 90 degrees. And we know that the sine of 90 degrees is exactly equal to 1. So we can solve for v here by dividing by qb. And then let's substitute in the numbers as I have shown here. So if we put in all the numbers as are presented earlier in the problem, we should have about 0.00204 meters per second to 3 significant digits. That's 2.04 times 10 to the minus 3 meters per second. Now, how fast is that really? Well, times 10 to the minus 3 is milli for the metric prefix. This is 2.04 millimeters per second. So that's moving quite slow. Thank you for watching High Peak Education. Please smash that like button if you enjoyed this content. Please share this video amongst your social networks, and please subscribe to grow the channel. I look forward to reading your comments, and I will see you in the next video.